This is pack 18. It's the last pack in B6. It's about learning and memory. Now previously we'd looked at the reflex arc. It's a simple involuntary action. It doesn't use any conscious control. It doesn't involve the brain. And it's in this simple example we've got a hammer touching the knee where there are receptors on the skin which detect the touch. They cause an impulse to travel along a sensory neuron which takes it to the central nervous system and across a synapse to a relay neuron. Now this relay neuron is connected via a synapse to a motor neuron, so it transmits an impulse to the motor neuron which carries the signal to the effector, which in this case is a muscle in the leg, and it causes the lower half of the leg to move upwards, and it straightens. Now this is a very quick response. It's just 3 neurons together and it's automatic and requires very little processing. Now animals can be trained or can learn to produce a response to a different stimulus, and this is called a conditioned reflex. Now the original work on conditioned reflex was carried out by a Russian scientist called Ivan Pavlov. He just observed things with a dog which he used to feed or bring feed to, and noticed the dog would salivate in anticipation of the food. But he also noticed the dog salivating even when he came to the dog without food. And he concluded that maybe the dog was associating him, his lab coat, with the food that he usually brought. And so he was responding in the same way to food when he saw Pavlov, even without food. To test this idea, he deliberately set up an experiment where he used a secondary stimulus, which in this case was a bell which he rang every time he brought food out for the dog. And the food itself was the primary stimulus, and it was the sight of the food that was the original reflex that the dog had and made him salivate and get ready to digest the food. Now Pavlov repeated this system, which is called classical conditioning, where he rang the bell every time the food came along. He eventually stopped bringing the food and just rang the bell alone, and he noticed that the dog was responding in the same way to the secondary stimulus, the bell, as he had originally done to the primary stimulus or the food. What had happened is the dog had learnt a new association between the bell, the secondary stimulus, and his reaction, which was normally to the food. Even though the bell really had no actual association with the food, it was just a coincidence. And this kind of modification to a reflex is the basis of a lot of complex behaviour that can be brought about by training animals. Now in your pack there's reference to quite a controversial experiment from a long time ago, where a little boy called Albert, who's only aged 9 months, was allowed to play with a pet white rat. He showed absolutely no fear for the rat, but after a while the researchers decided to do a kind of cruel conditioning experiment. So they introduced a primary stimulus of a very loud noise. It was actually smashing a piece of metal together. It caused Albert to be, frightened and cried. But they only make this loud noise when Albert actually touched the rat. Now this training was repeated many times, and eventually Albert became upset every time he saw the rat, which actually was the secondary stimulus in this case. And he became afraid of it even when there wasn't a loud noise. So again, Albert had learned to associate his reflex to the loud noise with the secondary stimulus, which was the rat, which he initially had not been afraid of. So his unconditioned response to the secondary stimulus, the rat, was nothing actually. He was fine with it and he showed no fear, but after conditioning, his response was fear and crying when he saw the rat. Now many reflex arcs are there because they are fast and they give a protection often from harm, but sometimes it's appropriate to be able to modify that reflex. For example, we might have a hot cup of tea in our hand, and the reflex action might be to drop the cup of tea, but if it's not too hot, we may wish to avoid dropping and breaking glass and spilling hot liquid, so we will modify that response and keep hold of the cup. So in this case, the hand has receptors on it which detect the temperature of the cup, which is very high. It stimulates the sensory neuron, which sends a message to the central nervous system. Now you're aware, probably you've seen the cup and you've felt it, and your brain sends a signal down to the spinal cord at the same time as the sensory neuron from carrying the message from the pain receptors in your hand to send a signal. And the impulse from the brain then modifies the original reflex arc and actually blocks the transmission of the impulse to the motor neuron that would have caused you to drop the cup. So we have a modification of the original reflex arc, which was useful and protective response, but our brain has intervened to stop us causing a different undesirable outcome where we broke the cup and the hot liquid was spilt. Now conditioned responses and modified reflexes are important because, as usual, they increase the chance of survival. There may be the case of a very bright coloured insect which initially sounds as though it's not very good, because we typically think that a camouflage insect is going to be the thing which gives the greatest survival advantage. However, an insect may have another defense, such as poison. Now, it's not useful for the insect to poison the bird or whatever after it's been eaten. So what can evolve is, say, a bright colouring in the poisonous insect, and that can cause a conditioned response in the birds. Where when they see a bright insect, it makes them feel ill. There's an association made between the illness or the bad taste and the bright colour, and next time the brightly coloured insect is avoided by the bird. It's a conditioned reflex to avoid the insects, and it gives a survival advantage to the bird. Now, mammals have billions of neurons in their brain, and they can develop very complex behaviours built on experience and interactions with their environment. The learning from new experiences basically involves the building of unique neural pathways. Now, initially in a baby, there's It's quite a low level of organisation in the brain. But over time, the experience of many different situations causes neurons to organise in different sort of circuits. Now, as the animal continues to interact, you might have the same experience again, and the same pathway is stimulated. And this repeated stimulation of a pathway actually strengthens it. And experiences that are not repeated, their pathways are lost. But repetition, it can help the animal learn new things, because these new pathways are repeated and strengthened and become more efficient. And it's this building of new pathways and creating these new networks which is the essence of learning in mammals. Now, in this simple diagram in your pack, it's just to illustrate that creation of new pathways. And on the left here in neuron 1, we've got perhaps a new experience that a baby may have sensed. It causes an impulse that stimulates another neuron, and then again after that a third neuron. Now, if this experience is repeated and this same simple pathway is followed from neuron 1 to neuron 2 to neuron 3, the connection between those neurons is strengthened. And given enough time, the stimulation of neuron 1 will lead to the stimulation of neuron 2 and 3, and this will be a fixed new pathway, which may be the basis of a new skill that the baby has learnt. And in the same way that new pathways can be made through the repetition of a stimulus or an experience, if something is not repeated, the pathway can weaken again, and in that way things which are not useful, skills which are not useful or not repeated or developed, are lost, and useful new repeated skills are strengthened. Now, the formation of these new pathways is particularly good in young children whose brains are in a state of really rapid development. And pretty much everyone has witnessed how quickly they can learn a language, and particularly it's believed up to around 8, young brains are particularly good at forming new neural pathways which help them learn language. And in this graph in your pack, we've got a comparison between a child who's exposed normally to other people and learning to speak a language, and in the square boxes, this is a child, and the boxes show the number of words they speak, who actually was completely isolated from other people until he was age 4. And as you can see from the squares, despite the fact he was exposed to people after the age of 4, his language progress was very slow, and by the age of 15 he really hadn't learned that many words, especially if you compare it to the kid who was exposed normally before the age of 4 to other people and who was speaking language. Now, this certainly isn't proof that if you're kept away from people you can't learn language, but it certainly indicates the possibility that there is a small window of opportunity in the brain's development which is particularly open to learning new languages and forming these new neural pathways which help the child develop language. Now, memory is a fairly complex subject, but we can simplify it by thinking about the idea of a multi-store model of memory. Now, a short-term memory is a very brief memory, only lasting 30 seconds or so. Which can be lost very quickly into forgetting unless the information is rehearsed or thought about again, or is particularly of interest to us. Now, this useful or interesting information, if we repeat it or relearn it, can go into a long-term memory which can last a whole lifetime, by which I mean you can recall it again at a later time, weeks, months, years, decades later. Now, really understanding memory is very difficult, but that's why scientists often use models to help them describe how things work. The problem with models is that they are useful in your understanding initially, but often they have quite some limitations which don't really explain all the details. Now, one of the most useful models of memory is the idea of multi-store memory, that there are several levels of memory, starting on the left here with the sensory memory, which is an extremely brief memory from your sight or your hearing or your smell or any of your sensory organs, which literally lasts a couple of seconds before it is forgotten and cannot be recalled again. Now, if you pay this sensory memory attention, if it has some interest to you, it may be kept in your short-term memory, but again, not for very long, maybe up to around 30 seconds before it is forgotten, unless it is rehearsed or repeated again in order to try and remember it and put it in long-term memory, which can last anything from a few minutes after you've first sent something to years or decades later. Now, in a way, the brain's very efficient, and if a memory is not rehearsed or recalled, or is not interesting or unique or frightening or in some other way remarkable, again, the memory can be lost and we forget something, and by forgetting I mean we are unable to recall that information again. But the importance of this rehearsal of memories is the very basis for revising, and we have to revise at suitable times after we've learned something new. We can't leave it for weeks or months. It's very useful to bolster our long-term memory to revise something very shortly after we first learnt it. And we're talking about even an hour, and then a day, and then a week, and then a month later. And this really consolidates the memory and puts it firmly in our long-term memory, where we'll be able to recall it for years later. So in summary, the brain is able to modify reflexes and process really complicated information in the formation of new neurological pathways, and the brain's able to store and retrieve information with its memory, and mammals are able to develop really complex behaviors through learning from experience, and this ultimately provides a species with a survival advantage, which they're able to survive longer, have more offspring, and pass on that complex brain which helps the species as a whole survive longer.